Let's turn our attention to the relationships between load, the shear, and the moment within the beam. External loads obviously cause shear and moment in the beam, but it turns out there's some mathematical relationships between these three things, and that's what we're going to be able to use by the time we're done with this lecture. In particular, we're going to look at distributed loads and how they relate to internal shear. Then we will consider how internal shear and internal moments within the beam material itself are related to one another. And then finally, we will look at the effects that concentrated external loads, both force and moment loads, have on the internal loading of a beam. There are many applications of these concepts, and here's an example where we've got a lateral beam that's supporting the deck of a roadway, and this beam has to not fail. We can't afford for it to fail, but look, there are many points of contact, so several places where load is applied along the length of this beam. And the point is that you can have a beam that has a fairly complicated loading scenario. How do you go about calculating the shear and moment within the beam if you have a lot of loads, a lot of external either forces or moments or distributed load even applied to the beam? What do you do? Because you really need to understand how the shear and moment vary within the length of the beam in order to determine where to put reinforcement, how big the beam needs to be, and so forth, so that it does not fail. So how do we deal with this? Well, it's really important that you understand how the shear and the moment and the external loads relate to one another on a little bit deeper and more mathematical level than what we've considered so far. So we're going to take a beam that has a fairly complicated loading scenario. You notice there's a distributed load actually acting upward and with non-constant magnitude. So you notice on the left-hand side of this beam at A, the distributed load is up but relatively small. It increases as we move past F1 and F2, which are themselves concentrated force loads, until between C and D it looks like the distributed load is relatively constant and upward at its maximum value until it goes all the way out to D. Now, another interesting load applied to this beam that's an external load is the concentrated moment M0 that occurs between C and D. So what we're going to do is take a section of the beam. Now notice we're being very strategic because it turns out anywhere there are external point loads, whether they are force or moment loads applied, it turns out we'll potentially have some discontinuities in our shear and moment diagrams. So what we're going to do is choose a section where all we have is some distributed load, or in a less general case, we would have no external loading in this segment. So we're between B and C. It doesn't really matter exactly where. We're somewhere between points B and C. Notice that F1 and F2 are outside of this range, as well as the moment M0. And in this region, we only have some varying distributed load, and that's indicated by the dotted lines in this little segment, this little free body we have pulled out of the beam. Because think about it, this bit of material is in equilibrium, right? It's not accelerating. So while we know there are forces on it, those forces have to somehow be balanced. And at first glance, you might say, well, the only force on it is part of the distributed load. How can that be in balance? Well, the rest of the beam that remains with B and the beam that remains with C, are themselves applying loads to this little segment, and that's what keeps this segment of the beam in equilibrium. So what kinds of loads can be applied? Well, of course, there are axial loads, but because of the pin supports and the roller supports that we have in this problem, the fact that there are no external loads in the horizontal direction, the compressive and tension loads along the axis of the beam are not useful. They don't do anything for us. Now, you can argue that there are compressive and tensile loads within the beam that make up the moment, but that's a topic for another class. For right now, we can think of it as shear on either face of this free body and moments on either face of this free body. Now, we're not claiming that the shear and the moment on both faces are exactly equal. As a matter of fact, they should probably be different because we have to somehow support the load that we have, right? Because we still have that external load. We still have W of X. This is just indicating a distributed load that varies as a function of X position along the length of the beam. Now notice the X coordinate begins at 0 at point A. So we've got this distributed load along our little bitty segment, and our little segment only measures delta X long. It's not very long. But on the left-hand face, we've got a shear upward V and a shear on the right-hand face that is different potentially, V plus delta V. Now, it could be less in magnitude than the shear on the left-hand face. Delta V, in other words, could be a negative thing. That doesn't really matter. The point is those two are different by some amount, delta V. And then the moment on the left-hand face potentially could be different than the moment on the right-hand face, because notice on the right-hand face we have an m plus delta m, where delta m indicates the difference between the magnitude of moment on those two faces. Now notice that instead of considering the distributed load on this little segment separately, what we've done is we've said, you know what, let's calculate the magnitude of that load as the distributed load, W of x times delta x. And what we're going to do, we're ultimately going to allow delta x to go down to 0. So even though W of x, the distributed load as a function of x, may vary along this little segment, we're going to let it shrink down until it doesn't. So we're just going to take some average value of this distributed load W of x and multiply that by delta x to get our resultant force F. And that resultant force might act at the center of this little segment, might act right above O, it might act all the way to the left side where the shear force V and moment M are applied. We don't know where, but we can quantify it or approximate it by saying, well, you know, there's some position. I mean, obviously this resultant has to act on this little segment. So we'll just multiply it by an unknown value k, where k will vary from 0 to 1. If k is equal to 0, then the position of the resultant force of this distributed load is directly above O. If k is equal to 1, then it's all the way at the left-hand side of this little segment. That's not terribly important for this slide. It'll be important later, because what we're going to do is simply sum forces in the vertical direction. So typical xy coordinate system, we're going to consider what happens when we sum forces in the vertical direction on this little bitty segment, this little sliver of the beam. Well, what do we have? Well, on the left-hand face, the moment applies, but wait a second, a moment doesn't cause a force in the vertical direction, so that won't appear in the equation. We've got the vertical force, the vertical shear force on the left face, V, that acts up. Now, notice that while V is acting in a positive sense for a shear diagram, in the equation, it appears positive because it's in the positive y direction. Okay, so we got that. And then notice that the force F is acting upward, so that's in the positive y direction, so we simply write W times delta x, or W as a function of x times delta x, indicating the effect of the resultant of the distributed load on this little bitty segment. And then on the right-hand face, we've got V plus delta V as shear on that face, and of course that is a positive shear for the sake of a shear diagram, but not in this equation, because this equation is summing forces with respect to the y-axis. The y-axis says up is positive, okay? So if we were to plot this shear on a shear diagram, and it was, you know, we had a positive value for V plus delta V, it would go on the positive side of the axis. But when summing forces in the vertical direction against or with reference to a y-coordinate, this is a negative direction. So we have to write minus the quantity of V plus delta V. But those are all of the forces that act on this free body, and those forces must be in equilibrium, because if they're not, this little segment's got to start accelerating. Now notice that the V has been written carefully and strategically on both sides of the face so that we can cancel it out in the equation. And all we're really interested in there, according to this equation, is the difference in the shear between the two faces. So we can rearrange it, move that delta V. Notice the delta V will ultimately be negative in the first equation. So we move it to the right, flip the equation around, and what we've got is an equation that tells us how much the shear changes from the left hand to the right hand face. Not surprisingly, the change in the shear is simply equal to whatever external load is applied, which is a certain distributed load, which we've added up into a resultant. So it's not really a surprise that we end up with this. You probably could have written that down just by inspection. Now, there's something really neat we can do here. What we're going to do is take the delta x and divide delta v by it. In other words, we're going to divide both sides of the equation by delta x, by the length of this little sliver. So what we've got is that the ratio of the change in the shear to the length of this little segment is equal to the distributed load. Now, sometimes people will write distributed load up as positive, sometimes down as positive, and it'll make this equation, they'll put a negative in this equation. For our textbook, we're using a distributed load up is a positive thing. So just get used to that. But sometimes in other references, you'll see it done the opposite way. So the sign's not all that important as long as you're consistent. And then if we allow the width of this little segment that we've taken to go to 0, well, then what we'll have is differential amounts. We'll have a differential change in the shear across the width, where we've got that divided by a differential width dx. And so this is the differential equation that relates a ratio, the rate of change of the shear with respect to changing position, to the distributed load. Now we can do something interesting with this equation. If we pull it over to the next slide, using the rules of calculus, we can separate out the two variables and integrate. So we put all of the shear variable, the variation in the shear on one side, and the variation in the width or along the length of the beam on the right-hand side, and then we can integrate between 2 points. So let's say we integrate from point B all the way to point C. Now notice we're not integrating across the forces, right? Whenever there's a point load, those point loads cause some special things to happen in the shear moment diagram that I'll describe to you later. But for right now, let's integrate from point B to point C. So if we do that on the left-hand side, we got to do the same thing on the right-hand side. On the left-hand side, our limits would be shear limits. So the value of the shear at B and then the value of the shear at C would be the upper limit. But on the right-hand side of the equation, the value at B would be the X position at B. In other words, what is the length of B with respect to A? What's the distance between A and B? And then C, that limit, that position or that state would be the X position of point C. It's that simple. So that's what we would integrate across. And when you do that, what you'll find is you'll simply get the change in shear from point B to point C. Because look at the left-hand equation. We are simply integrating the differential of a variable. And so we know that we must get back the change in that variable. And that's why we have delta V, the change in the shear from point B to point C. Now, forgetting about the B and the C and just assuming that we're always going to apply this equation to 2 points where we don't have any point loads between the 2 points, we can write in a more general sense that the change in shear between 2 points is the integral of the distributed load along the length between those 2 points. And that's a really important equation. You'll see me apply that in the example problems. But we kind of skipped over something, didn't we? What else could we have done with that little bitty segment? Well, let's extract that segment again and look at it. What else could we have done? Well, wait a second. We summed forces. Couldn't we also sum moments? We could, in fact. So let's sum moments about point O, which is on the right-hand face. Now let's see. If we sum moments about point O, you notice that the shear plus delta V on the right-hand face, that passes through O, even though we draw it off to the side a little bit. It actually passes right through the face. So it has no moment arm about O, whereas the shear on the left-hand face certainly does have a moment arm, and that moment arm is delta X. But let's not forget we're summing moments, and so what we need to write first is the moment on the left-hand face. Now be careful. I know that by our sign convention, both these moments at the outside edge of the beam are positive, but that's only for the moment diagram. In the sense of the XY coordinate system that we're using, the moment on the left-hand face is a negative moment, right? Because moments counterclockwise, X cross Y, are positive, okay? So, or our sign convention that we've chosen in summing moments is that counterclockwise is positive. So that moment on the left-hand face, that M written in blue, is a negative moment, whereas on the right-hand face, the moment plus change in moment on that particular face are both positive values, and so that's how they appear in the equation. Now remember, we're summing moments about point O, and we need the moment of the resultant of the distributed load. Remember, the resultant of this distributed load F is equal to the distributed load itself for this position multiplied by the width of this little sliver that we've taken out of the beam. And of course, again, we're going to allow that sliver to go to 0. So we're not too worried about, the fact that the distributed load is a little lower on one side than it is on the other. As we allow the segment to go to 0, the distributed load is just going to go to one value. So we're not going to worry about that small difference. So if we take the distributed load multiplied by delta X, well, that's the resultant of the distributed load. That's F. But that moment, or that force, that resultant force, will have a moment about O depending on how far out along the length of the beam that force acts. So remember that we've got K delta X to quantify the position of the resultant force F. And of course, K varies from 0 to 1. If K is 0, then the resultant acts right above O. If K is equal to 1, then the resultant acts at the extreme left-hand face of this little segment. But of course, if, sort of a sanity check here, if the distributed load, we're actually itself uniform and the same on either side, regardless of what size we took. Then we could say that K would definitely be a half, because think about it, the resultant would have to act in the center of a uniform distributed load. So hopefully you understand what K is doing for us. It's just a placeholder, basically, while we need this term in the equation. So that next term, it looks a little complicated. The term in square brackets is just the resultant force F that represents all of the distributed load added together. And then K delta X is the moment arm of that distributed load resultant. Finally, the shear V acts away from O, and so it has a moment arm. Its moment arm is obviously delta X, and if you look at it, that shear acts upward, and so the moment of an upward shear times delta X would be a clockwise sense, which is opposite to our chosen direction, so we write minus V delta X. So now what can we do? Well, the first thing to do is to notice that those two M's are equal and opposite. Really what we're interested in is the difference in moment between the two faces. So those two cancel each other quite nicely, and then we can rearrange to solve for the change in moment from the left-hand face to the right-hand face. And all we've done is collected some terms together like delta X. We've got delta X squared, and of course the sign on the front of these have changed because we moved them to the other side of the equation, and I put a dot in there to get rid of those square brackets. But we still have W as a function of X times K times delta X squared plus V delta X. Now, as we allow the width of this little sliver to go to 0, what's going to happen with that first term, WK delta X squared? Well, delta X is going to go to 0, so that one's gone. But wait a second, before we do that, it seems like that second term would disappear too. So why don't we divide by one value or one variable, delta x? We'll divide a delta x out because it appears in both of those two terms. And then what do we have? Well, the first term, wk delta x, still has a delta x in it, but the next term does not. So now when we allow that delta x to go to 0, that first term, wk delta x, will go to 0, and we'll end up with the equation we came for, which is the rate of change of the moment with respect to a change in position is equal to the shear as a function of position along the length of the beam. So really the shear represents the slope of the moment graph. This is really important because when we make a shear and moment diagram, what this tells us is that whatever the slope of the moment graph, it's going to be predicted by the magnitude of the shear graph. So all we have to do is look at the shear graph, look at its magnitude at any point, and that must be the slope of the moment graph. And so that's a really helpful piece of information when we're trying to come up with these shear and moment diagrams. Now, bringing that equation into the next slide and working with it a little bit more, we're going to play the same game we did before. We're going to separate out the variables so that we can integrate them. Notice the shear is just a function of position along the length of the beam. So everything on the right-hand side of the equation is as a function of x. Everything on the left-hand side of the equation is as a function of moment. In fact, it's just the differential moment. And when you integrate the differential of a variable, you simply get the change in that variable back. So what this equation does, if we were to integrate from point B to point C, it would give us the change in the moment from point B all the way over to point C. It wouldn't tell us the magnitude of the moment, but it would tell us how much the moment changes from B to C. And so the really important relationship here is that the change in the moment between 2 points is the integral of the shear. Now, what does that mean in terms of shear moment diagrams? What that means is that if we want to know how much the moment graph changes, all we have to do is look at the area under the curve represented by the shear graph. So we just look at the shear graph, look at the area under the shear curve, and that'll tell us how much the moment changes. So this is a nice relationship between the shear and moment diagram that we can take advantage of when we're trying to create both diagrams. So while those are general expressions that we've derived, what happens when you've got point loads? In other words, what happens when we have to cross a point load? What do we do then? Well, let's consider what happens. Let's take a bit of beam material right underneath a force, like for example F1. Now in my case, I'm going to take the force up. In the example, the force is down. It doesn't really matter. Remember, we're going to take force up as a positive thing. So that's why we're working with it. But the question is, what happens to the shear diagram? What happens to the moment diagram when we have a concentrated force like this? So remember, we're always going to let this little segment go down to 0. And so I don't have any distributed load because as this goes down to 0, we're not going to have any load at all from the distributed load, so why bother? What happens is pretty simple. We're going to sum forces first of all to see what would happen. And of course, we're letting these sides crush in so that we always contain the point force F. So if we sum forces in the vertical direction, what happens? Well, on the left-hand face, we have upward shear. On the right-hand face, we have a negative shear plus delta shear. So those two terms appear. That's the first and third terms in the equation. And then the external force F acts upward. And we'll go ahead and include the contribution from the distributed load, because as long as we've got some delta x, there would be a resultant force. But of course, all we're going to do is cancel the two shears and only look at the difference between the shear on the two faces. And then, of course, as delta x goes to 0, that last term in the equation goes away, and all we end up with is that the change in shear is equal to F. And so all that means is when you're working along on a beam and you get to a concentrated load, all that concentrated load is going to do is change the shear. That's all it does. It just makes it move directly up or directly down. And you'll see me use this idea in example problems. Well, what about a concentrated moment? What would that do to our diagrams? Well, let's take a segment from where a concentrated moment is applied and let's consider it. So we've got this concentrated moment here, and we're going to do the same thing we did with a concentrated force. We're going to let delta x go to 0 so that we include that moment. And of course, there will be potentially different moments on the left and right face, different shears as well. And we're going to sum moments. And I haven't chosen a particular point here because it'll turn out that it won't really matter. If we go ahead and sum moments about the left-hand face, for example, then that'll match the equation. So think of it that way. I don't know why I didn't choose the right-hand face like we did before, but we don't have a point O here, so it doesn't really matter. So left-hand face is what we're summing moments about. So we've got a moment on the left-hand face that, according to our XY coordinate system, is a negative moment, or according to the sign convention I've chosen. When I said the sum of moments are equal to 0, well, they have to be 0, otherwise this little segment would start to angularly accelerate or turn. And so the moment on the left-hand face is negative in our equation. The concentrated moment itself, m naught, is also in the negative direction. It's in the clockwise direction, so we write negative m naught. And then the moment on the right-hand side face, both the moment and the difference in moment are both positive, so we write those as positive. And then we have a moment due to the shear on the right-hand face. That's going to end up going away, but for the sake of completeness, I've included it. Now notice that the moment on the left and right-hand side face cancel, except for the difference in the moment on those two faces. So those two cancel each other out. They're not 0, but they just cancel each other out because one's positive and one's negative. And of course, we're going to let the width of this segment go to 0, and so that delta x goes away. And all we end up with is something kind of simple. Concentrated moments simply change the magnitude of moment on the graph. So it can cause a discontinuity in the moment graph where the graph jumps vertically up or jumps down, depending on the direction of the concentrated moment. And you'll see me use that in example problems as well. Now, there are some really important points that won't make any sense to you right now, so I'm not going to read through these. I'm not going to ask you to even, maybe read them in the slides. Print these out like you did before with the last lecture, and keep these to the side or keep the slides open to the side. And as you see me go through example problems, look for me using some of these principles, because you need to understand them and you need to get used to using them. They're really simple once you understand what they say, but it's easier to understand them in the context of examples than to read through them now and try to figure out what they mean. There's another list here. There's a second list of principles, if you will, important points that are very useful in working these types of problems where you're trying to make a shear and moment diagram. They're just principles of relationships between the loading, the external loading, I should say, the internal shear, and the internal moment. But again, they won't make a lot of sense to you right now. Keep them open to the side and look through them as you watch the example problems and see if you can spot where I'm using these various principles.